Well, good afternoon, my lovely chemistry students. Hey, so you are here so that we can get to the bottom of topic 3.2 B and C CFA. So this is stoichiometry, limiting and excess reactants, and percent yield. Now, just a reminder, every year this is troublesome for a lot of students. But every year, those same students who find this troublesome eventually figure out if and only if they stick with it. So Mr. Huderberg knows you guys, each and every one of you, and he knows, doesn't think, he knows every single one of you can get this figured out if you give it the amount of time it needs. All right? So with that said, I'm going to walk you through each and every question on the CFA as we prepare for next week's assessment. So let's take a close look at number 1 here. It says use the following reaction. This is a combustion reaction. C2H6, by the way, is methane. Okay, so what we have to remember, this first question, multiple choice question, is do you really understand what a reaction is telling us? And what's important to us in these balanced reactions are these coefficients. Okay, that we spent a lot of time learning why we need those to balance out conservation of matter, etc. Okay, so we've got those coefficients, 2, 7, 4, and 6. And all that does is it tells us a ratio. Okay, so on the molecular scale, it tells us 2 molecules of ethane react with 7 molecules of O2. So it's that 2 to 7. Okay, but we have to remember that a molecule of ethane does not weigh the same as a molecule of oxygen. So we cannot compare our gram amounts. So we can eliminate letter I right there. That's why we have to convert to moles whenever we do stoichiometry in the first place. So it's definitely not letter I. It definitely is that one. Now, we also have to remember that we can't see or measure or count molecules. They are far too small. And the beauty of the unit moles is it allows us to essentially use the same exact numbers, but in a quantity that we can measure. Okay, so grams are important. We weigh things in grams. We convert that to moles so that we can use the same coefficients, same numbers for molar mass, formula mass, whatever, to do our calculations. So the correct answer, number 1, is letter E, I, and II. So this is telling us how many molecules of each, or in a laboratory setting, how many moles of each. That's the beauty of that unit moles. Okay, so how many molecules? Something we can't see or measure or touch, but we can model, or actually how many moles, which is something we can see, measure, and touch in a laboratory setting. So both of those work. All right, let's move on to the actual math itself. Okay, so moving on, now comes the actual calculation piece. So we want to understand conceptually what's going on. We also want to show what this looks like. How can we use math to predict things in chemistry? Again, if we can't make accurate predictions in chemistry, we might as well not do it. It is pointless. That's the test of a good scientific theory. Okay, so in number 2, let's take a look. And again, I want you guys to pay close attention to units here, because I want you to see in number 2 that our number, 3.25, it's already in moles, which means we don't have to do any converting. And it asks us to calculate our answer in moles. So we don't have to do molar mass of anything for this particular question. And lots of you guys, by the way, did great on this one. So if we have actually 3.25 moles instead of 2 of this, how much CO2 should we get? All right. So what matters to us is that 2 ethane to 4 CO2 ratio. So all we do is we take the actual amount we have, 3.25 mole of C2H6. All right. I like to put that in a little fraction over 1. And I'm going to multiply that by the mole ratio, which, again, what starts at the beginning? I have C2H6 on top over here. I'm trying to convert the number of moles of that to CO2. So whatever I start with goes on the bottom. So this is 2 mole C2H6. for every 4 mole CO2, right? So whenever we're doing a mole to mole conversion, it's one step. We look at our balanced reaction, identify our coefficients for the two things we're comparing, and multiply, right? Whatever we start with goes on bottom. Whatever we're trying to figure out goes on top. So lock that in, please. And then all I'm doing essentially is multiplying 3.25 times 4 over 2, or 3.25 times 2, and I should get 6.50 moles CO2, right? And I get to do the fun part of canceling out that part. All right? Number 3. Now, it says calculate the minimum amount of oxygen in moles. So my answer is going to be in moles. Required to completely combust 35.47 grams of C2H6. So again, we need to pay attention to units, and we can't do a gram to gram comparison. We have to convert to moles. So this number needs to be converted to moles first. Okay? So I have 35.47 grams of C2H6. I'll put that in a fraction over 1 times. All right, so first step is convert this to moles. So that has all right, so we have a molar mass for C2H6. I'm not going to show you how to do that. For crying out loud, you should know how to do that, which is 30.08 grams. So that is 30.08. Okay, so I know that 1 mole of ethane, C2H6, has a mass of 30.08 grams per mole. Okay, so then I'm in moles, right? So I could just stop there, hit equals to get the moles. I'm going to keep on going because my next step is to also multiply by a mole ratio. So this is going to save us some time. So that converts from grams to moles. Now I'm in moles of ethane. I need to figure out how many moles of oxygen that looks like. So 2 moles of ethane require 7 moles of oxygen. Cross off moles of ethane. And now on my calculator, I just go 35.47 times 7 divided by 38.08 divided by 2 equals, and I should get, with some rounding, 4.13 moles oxygen. Okay? Now, last one, number 4, is my answer needs to be in grams. My starting quantity is in grams. So that means I'm going to have to do what I just did here, plus one more step of converting it back to grams. So, amount of water in grams produced when 43.89 grams of CO2 are produced. So, I'm going to use these two numbers right here, 6 and 4, for my mole ratio. But first, let's convert this number to moles. So I have 43.89 grams CO2. So that's how much over here was actually produced. Put that in a fraction over 1. Convert that to moles by dividing by 44.01 grams per 1 mole. So that cancels out. Grams gets me to moles. Now I know I need my mole ratio here. 4 CO2 produces 6 H2Os. So when I have this combustion reaction, if there are 4 moles of CO2, I get 6 moles of water. All right, but I want my answer in grams. So that would tell me moles of water if I stop there. Next, I am going to go convert, well, in 1 mole H2O, there are 18.02 grams H2O. And boom, boom. And when I multiply 43.89, let's just say 43.89, write that a little better, times 6 times 18.02 equals, divided by 44.01 equals, divided by 4 equals, I get, with rounding, 26.96 grams of H2O. Okay, so notice, by the way, I'm not just putting the number, I'm putting the unit and of what? So moles of CO2, moles of oxygen, grams water. All right, moving on to part 2. So it says use the following reaction. So we got iron and hydrochloric acid reacts to form iron chloride and hydrogen gas. Okay, so a chemist has prepared 3.24 moles of iron and 6.79 moles of HCl. Identify the limiting and excess reactants. Remember, we need to know what the limiting and excess reactants are because the limiting reactant tells us how much we get at the end. So that's meaning it's the one that's going to run out first. So which of these? Is it 3.24 moles of iron that's going to run out first or 6.79 moles of HCl? All we have to do, okay, is identify which one, iron or HCl, is going to run out first. Okay, and in order to do that, we just pick one of these numbers to start with, okay, to identify those. Now, there's lots of ways, lots of different methods that all do essentially the same thing. So let's just do this. Let's just say I have I'm going to use my 3.24 moles of iron as my starting point. 3.24 moles of Fe, that should be a 4, okay, over 1 times, so how much HCl do I need in order to use all of that iron up? So I'm just going to go to Fe for every 6 HCl, right? And what that'll do is that'll tell me how many moles, I should not have crossed that off, excuse me, how many moles of HCl would be used to use up all of that iron. Okay, so I'm going to go 3.24 times 6 divided by 2, and I get 9.72 moles of HCl. All right, so this number, using my mole ratio, tells me how much HCl I need. Okay, I have 6.79 moles. Okay, so that means I don't have as much as I need. So this tells me then that if I mix these two together, there will be a reaction, yes, but I won't use up all the iron because the HCl runs out before the iron does. Because in order to use all of that iron, I need this much HCl. I only have that much. So I don't have enough HCl. So my limiting reactant is HCl. My excess reactant, therefore, is iron. Okay? Now, moving on. Next question is calculate the amount of excess reactant remaining after the reaction has completed. So in order to do that, okay, so, when I do these, predicting like how much gets used, how much is left over, we always have to use our limiting reactant we just identified, right? So it says calculate the amount of excess reactant remaining, so how much of that iron is going to be left after the reaction is completed. Again, remember we started with 3.24 moles of that iron. So how much of that is left after the reaction is completed? Well, we have to calculate how much our limiting reactant uses up. So we're going to go 6.79 moles HCl over 1 times 6 HCl for every 2 Fe's. All right. And when I do that, I get 2.26 moles of iron. Okay, now that's how much is used. Okay, so keeping in mind we started with 3.24 moles. We react 2.26 moles of that, so there's going to be some left over. So all I do next is go 3.24 moles minus 2.26 moles, and I get 0.98 moles of iron remaining. Oh, okay. And number 7 says calculate the amount of iron chloride in moles that will be produced in this reaction. So all we're going to do is the same thing, but we're just predicting how many moles of iron chloride. So again, everything's already in moles. Our answer needs to be in moles, so we don't need to worry about molar masses. Okay, so for this one, again, we use our limiting reactant, 6.79 moles of HCl over 1 times mole ratio 6 HCl for every 2 FeCl3. Hey, I'm going to get a very similar number to that. Oops, here, 2 FeCl3. South HCl, and I'm going to get 2.26 moles of FeCl3. And I did notice on the CFA, some of you guys noted that this number of moles of iron is equal to the number of moles of iron chloride. Okay, and so you just made an equivalency there. That also counted because you showed proper mathematical reasoning, so that counted as well. All right. Now, last, certainly not least, we have our percent yield. So number 8 here was just sort of a gimme. Do you remember how to find percent yield? What's the formula? So we have actual or experimental yield over theoretical times 100%. Okay, so we were produced. That's how much we actually got. So I'm going to go 0.70 grams H2 divided by what we ought to have gotten if everything went perfectly, 0.98 grams H2. So what percentage of the 0.98 we should have gotten is 0.70. Multiply that by 100%. And we're going to get 71.4%. Skadoosh. Okay? Now, more often than not, right, we have to do stoichiometry first to figure out what that theoretical yield ought to be. So here is a familiar reaction. This is the one we did in the lab. We did baking soda and hydrochloric acid, and we made sodium chloride and some water and CO2. So that was those bubbles we saw. We evaporated that water off, and then we found the mass of that sodium chloride. That's that lab we did earlier, the end of last week, and finished on Monday. Okay? Now, let's take a different scenario. So let's say a student uses 24.3 grams of NaHCO3. That's in grams. So always, first thing we're going to have to do is convert that to moles. So 24.3 grams NaHCO3 over 1 times. Now, it says excess HCl. That means we're going to use up all the sodium bicarbonate. There's going to be some HCl left over that we don't have to worry about. We want to know how much the limiting reactant produces of something. Okay? So, molar mass of NaHCO3 is 84.01 grams per mole. That'll give us moles of NaHCO3. Okay? Then, I need to use my mole ratio because I'm trying to figure out how much NaCl I should get. So it's a 1-to-1 ratio. We'll put this here just for good measure. 1 NaHCO3 for every 1 NaCl. Okay, that'll tell me how many moles of sodium chloride we should get. And then I'm going to multiply that by molar mass of sodium chloride. So in 1 mole, there are 58.44 grams. And that will give me 0.2892 grams of NaCl. Okay? So, excuse me. That is not at all correct. That will give me 16.90 grams NaCl. So, this is theoretical. All right, so whenever we calculate an answer, that's our theoretical value. Our actual value is 14.24. So now that we know our theoretical value, now we can do our percent yield, which is just going to be our actual. This is how much we actually measured. Grams over 16.90 grams times 100%. And that gives me 84.26%. Bam. Okay, so all we're doing with percent yield calculations is stoichiometry first to get our theoretical yield, taking how much we actually got, dividing it by how much we ought to have gotten if everything went perfectly, multiplying by 100%. One more. Here we go. Here we go. So our synthesis question. So let's go back. Right? We got the same reaction right here. We got 24.3 grams of NaCl3. So our first step is going to be this same step right there. So we got 24.3 grams NaHCO3 over 1. Convert that to moles by going 84.01 grams per mole. All right, and that's going to give me 0.2892 moles NaHCO3. Okay, now we don't need to worry too much here because it's a 1-to-1 ratio, right? So that's also going to be 0.2892 moles of hydrogen. And again, the reason why that occurs is in our reaction, 1 mole of this also produces 1 mole of water vapor. Okay? 1 mole of carbon dioxide. Let's go back there. Sorry about that. 1 mole of sodium bicarbonate, 1 mole of water. So it's a 1-to-1 ratio. So if we know how many moles of sodium bicarbonate we have, we know it's the exact same number for moles of CO2. Sorry about that. Making you guys dumber. Okay? Because that 1-to-1 ratio. Now, the synthesis part here is, hey, let's go back to our ideal gas law, which is PV equals nRT, pressure, volume, moles, gas constant, temperature in Kelvin. So we can rewrite that. I'm solving for V equals nRT over P. So now I just substitute values in. V equals 0.2892 moles times R, which is 8.31 liters times kPa over moles times Kelvin times the temperature. That's in Celsius, so plus 273 makes that 295 Kelvin, divided by our pressure, which is 100.24 kPa. And we get a final answer equal to 7.05 liters CO2.